object at object when the object is exactly 2f away from the lens. So in this case it's 6 centimeters away from the lens. That's a distance of twice the focal length away from the lens. When it's exactly 2f away, I go through exactly the same steps. I draw a light ray which has been scattered from the top of my object parallel to the principal axis. Remember, because it's a converging lens, it gets converged through the focal point, so I go this way. That's the first ray, step number one. Step number two is to go through the middle of the lens. A light ray scattered from the top goes straight through the middle of the lens and doesn't get refracted. And hey presto, what do you notice? The image is produced, or should be, exactly on the 2f mark on the other side of the lens. Things to note, I would normally do a third line as well, as we showed before, but there's actually, you only have to do two rays, but you might want to just do the third one, the one that goes through the near focal point and gets refracted parallel to the principal axis. They'll all go through this point. So if your object is exactly twice the focal length away, let's describe the image. Well, it's inverted. The crucial thing is, this is 2 centimeters tall, and so is this. So at 2f from the lens, the image is inverted. It's the same size. It's the same size, and it's real. Okay, because again, it can be projected, and real rays of light produce it. So what would we use this for? Well, when do you want to produce an image that's exactly the same size? It's when you're on a photocopier. Okay? Focal point away and done. So, sorry, not image. What if our object is? So let's put our object. Here. I'm going to make it quite small. We'll see why in a second. So it's 6 millimeters high according to my scale. I go through exactly the same process. First of all, I consider a ray of light scattered off the top of the object that travels parallel to the principal axis. What would happen to that? Well, that object would be refracted through the principal axis, like so. Bear with me. So it would be scattered through the focal point, sorry. So it would be scattered through the principal axis at the focal point, because this is a convex lens. It converges the light, parallel beams of light through the focal point. Step two, I'm going to draw the scattered beam of light which goes through the middle of the lens. Again, it doesn't get deviated, so bear with me. Slightly difficult because I think my board isn't aligned properly. Straight through and there. And then I would do the third one, but as you can see, it's going to be quite difficult to draw. Don't forget my arrows to show that they're beams of light and which direction they're going. Now you'll notice that they cross about here. So my image would be produced here. Let's describe the image. It's inverted, upside down. It's inverted. It's real, because real rays of light are producing it, and it can be projected on a screen. It's real. And this time, it's been magnified, hasn't it? It hasn't been diminished, it's been magnified. Use that equation we said before. Magnification is image height over object height. And so it would be 0.6 all over 1.6, which is going to be greater than 1. I haven't got my calculator on me, but as you can see, the magnification is going to be greater. When do we want to produce an image which is bigger than the original? Well, a projector. Think about a projector. It's much smaller than the picture. I just want to show you example number 4, special case, when the object is at F. Okay, I've gone through exactly the same process. I'm not going to show you how I drew it, but exactly the same process. Parallel beam goes through the focal point, one that goes straight through the middle. notice that these guys are parallel. Okay? So when the object is actually at the focal point of the lens, so it's this distance of f, focal length away from the lens, what you get is parallel beams of light being produced, which means that they're never going to converge, which means you're never going to get an image. You're never going to produce an image. Now, why is that useful? Well, this is how spotlights are made. So imagine those very powerful spotlights you get at the theatre when they focus the light on one person and you get very straight beams of light. This is how they do it. Very clever. Example number 5. We're going to do when the object is next to the lens, but crucially inside the focal length. So it's between f and the lens. So what happens when the object's there? Now, again, we just go through the exact same process. Watch. Okay. We draw a parallel beam of light to the lens. We then draw one that gets refracted through the focal point, which is just the standard physics involved. We add our arrows to show that it's a beam, and then we draw one that goes through the middle of the lens. You will note that the rays are now diverging away from each other, which means again we're not going to be able to produce an image. But crucially, and this is the important part, is if I was to put my eye here, okay, I would actually see an image if you think about it, because look at the way these rays are coming. They look as if they're originating from a point back here. So what I'm going to do is I'm going to extrapolate my rays backwards, okay, as if to show where they are coming from. Now note how I'm drawing these as a dashed line. That's very important. And I'm going to do the same with this one. Okay, and that's where they cross. So that is where I would see the image being produced. Now, if you think about it, it makes sense that my eye would perceive these rays as coming from this point. So my eye perceives the top of the image to be here, which means that if I was to describe this image, so go back to the description, first and foremost, it's actually been enlarged, it's been magnified, it's been enlarged. Okay? Again, I could use the magnification rule, so image height over object height. So it would be image height is 2 over object height, which is 1, so it's got a magnification of 2. It's a ratio, no unit. It's enlarged. The object is the right way up. It hasn't been inverted, so it looks the same way up. I wouldn't get mirror writing, for example. So it's the right way up. And thirdly, and this is the most important thing, this is an example of what we call a virtual image. Okay? This is a virtual image. Now, what do I mean by virtual? If you look at the examples I showed you before, you'll note that the image is actually produced by real rays of light, and I can project it onto a screen. There's no way I can project this image onto a screen because the real rays of light are diverging. They're never going to be able to converge in one point. But I can see that image, and it's back here, but it doesn't exist. There are no rays of light back here. It just appears that there is. So it's a virtual image. It's like a mirror image is a virtual image as well. The actual image doesn't exist. It just appears that it exists in this place. So this is an example of a virtual image. And what is this an example of? Well, clearly it's a magnifying glass. It's a magnifying glass. So there's my magnifying glass. That's how to draw the ray diagram from a magnifying glass. Thank you.